This is TMUA 2019 paper number 2. The first question is about binomial expansion. Firstly, I'm going to write 1 over x as x to the power minus 1. And secondly, I don't need x to the 4 terms. Because I have this x squared term, I want x squared terms from this object, because then, of course, x squared times x squared gives me x to the 4. So I'm just looking for x squared terms in this object, ignoring this thing out here. Okay, well, I'm just going to use binomial expansion for that. So I'm going to take this to the power 6 first. Then it's going to be 6 choose 1, 5 of those and 1 of those, and then 6 choose 2, 4 of those, and then 2 of those. And this is actually going to be the coefficient that I want, right? Because that's going to give me an x to the 4 times x to the minus 2, which is an x to the 2. Anything more than that is going to give me a lesser coefficient, and these coefficients are too high. So it's this term that I want. 2 to the 4 is 16, that's nice and easy. 6 choose 2, well, n choose k is n factorial over k factorial, n minus k factorial. So 6 choose 2 is 6 factorial over 2 factorial, 6 minus 2, or 4 factorial. 6 factorial is 6 times 5 times 4, and so on. 4 factorial is going to be underneath, and it's going to cancel with everything that's left up here. So that chain cancels with that chain. You get 6 times 5 divided by 2, which is 30 divided by 2, which is 15, and then it's just going to be 15 times 16, as said before, to get me my coefficient of 240. Knowing how to do these choose functions without a calculator by cancelling factorials is super important, so do practice that. Number 2, this is funny. This is genuinely, so I've done the 2020 paper, I've done videos for the 2020 paper before the 2019 paper, and this question is identical to a question in the 2019 paper. Like, it's not similar, it's identical. The answers, the options for answers are different, aside from obviously the correct one, but the question itself is identical to question number 2 from 2020 paper number 1. They were just apparently feeling incredibly lazy. Anyway, it's just factor theorem. If x minus a is a factor, so if this is a factor of that, then f of a, in this case 2, is 0. So f of 2 is 0. If you put it into a 2 into here, you get 0 to give you this thing. This is a little bit more complicated, but essentially to modify this, you're just saying, well, what number do I need to put into here to make this 0? And that's going to be minus a half, right? So f of minus a half, putting into here, is also 0. Simplify that, times it all by 4, and we get a simultaneous equation, right? Put those together, solve it however you want to, I don't care. You solve for q, then you put it back into solve for p, and then you put both expressions into here to find the value of 2p plus q, and you get your answer. Good. Question number 3. Which of these must be true? So counterexamples. When you're thinking about things that whether something must be true, just think of counterexamples. I know now a equaling 0 makes this true, for sure, because it will be 0 equals 0, but it doesn't have to be true. Like, I could just choose a to be 5, and as long as b and c are the same, you get the same answer. So that doesn't have to be true. This, I've just counterexampled, like I've already got one. So, I mean, I apparently decided to write a different one, but I already had a counterexample to that one. Don't know why I wrote another one, but yeah, no, that doesn't have to be true either. And this one, b equals c, I think that's my counterexample for that. Maybe, oh, I just wrote that one again. What am I doing? Sure, well, there are 3 counterexamples for each of these 3 things. Nice and easy. None of them have to be true. If they are true, then sure, it might work, but they don't have to be true. Number 4, if n is a positive integer, okay, let's read this carefully, that consists of the digit 1, so all of these consist of the digit 1, followed by an odd number of 0 digits. Now this here has an even number of 0 digits. So this statement is not talking about this one here. It says, if n is a positive integer that contains 1 followed by an odd number of zeros. That's not this. This doesn't qualify. So immediately this cannot be either a counterexample or an example, like, because the statement just isn't talking about it. Okay, the other 2, though, have an even number of zeros in between the 2 ones. This one isn't prime because it's made up of this times this, so that's a counterexample. This is prime, so it's not a counterexample. It just agrees with the statement, but that is. Cool. Number 5, counterexamples, or examples, I guess. So ab is divisible by n. The condition either a or b is divisible by n is necessary or sufficient or whatever. Okay, here's an example of ab divisible by n. So ab, 15, 5 times 3, is divisible by 15. I know that. But when I come to this, either a or b is divisible by n. Well, neither 5 or 3 are divisible by 15, mostly because they're both smaller than 15. So this here cannot be a necessary statement, right? Because it just doesn't, this example here just doesn't even make it work. So this is not necessary. because this works in this statement, but it doesn't work for that. So yeah, I can get rid of those. Now this example here, I've chosen 5, 3, and 3. So 5 times 3 is 15, which is divisible by 3, so that's good. And now this also agrees with this. Either A or B is divisible by n. Sure, B is. 5 isn't, but it doesn't matter. It says either. So 3 is, which means this is, and I think we can logically say that it is going to be sufficient, because when you say that you've got one number that's, one of your A or B is equal to the number n, when you multiply these together, you're still going to have that factor around, which is just going to cancel when you divide it by this, and you'll just be left with this number. Or if B was like 6 in this case, we still have a factor of 3 in here, which would cancel with that, and we'd just be left with a whole number still. So I think it's fairly obvious that if you just choose A or B to be n, then you get a sufficient statement. This is fine, and then it's sufficient. So I think it's fairly clear that it's B there. Cool. I don't know why I repeated that slide. That's weird. Okay. Question number 6. A student attempts to solve this. Where's their mistake? So let's go through this slowly. They start out with something quite complicated, sure. All they've done here is they've moved the 2 sign over and split it into 2 separate pieces. I guess I'm okay with that. That's allowed. Then they've done some factorizing. Okay, well, this isn't immediately obvious why it's okay, but sine times minus 1 gives you the minus sign, so that's good. Sine times by tan is the sine tan. Cos times tan, well, sine divided by cos is tan. So therefore, sine is cos times tan. So that's giving you the other negative sign. And then minus cos times minus 1 is the plus cos. So this isn't at all obvious, this factorization, but it is correct. Oh, and we have just wasted all of our time because line 3 is so obviously incorrect. Okay, so what they've done here is they said, there's a bracket equal to minus 1. Therefore, each of the brackets must be minus 1. No. Okay, so this works when the thing is 0, because you've got 2 things multiplying that make 0, and the only examples you can come up with is 0 times something else, or something else times 0, or 0 times 0. But in any case, one of the things, or both of the things, are 0. So you set these to be 0. X plus 2 is 0 gives you the answer of minus 2. X plus minus 4 equals 0 gives you the answer of 4. But here, you've got 2 things multiplying to make minus 1. And an absolute ton of things multiply to make minus 1. Not just, and I mean definitely not minus 1 times minus 1, which definitely don't even do that. But like, 2 and minus a half would. So you can't set these brackets or anything when it doesn't equal 0. So that's the mistake. Good. Question number 7. Which of these is a counterexample? So, okay, so we've got some squares adding together. Nice. If A and B is satisfied and the 3 numbers have no common... Okay. So this is not anything to do with this statement, because while it has this bit, this bit is the same. It says, and the 3 numbers have no common divisor, but these do. These have a common divisor of 4, I think. So this is nothing to do with this statement here. So it can't be a counterexample whether it agrees with the next thing or not. It doesn't look like has anything to do with this. And at first glance, I didn't think it did either. But actually, this 16 you can write as 4 squared. And then, of course, you can multiply out the powers and you get this, which is a version of this, right? So, and here are some solutions. So this is actually, despite the fact it's in the wrong form, is a perfect counterexample for that, which is good. Moving on. Question number 8. Which of these following statements must be true? Now, again, must be true. So I'm going to try and come up with some counterexamples to them. The problem is, when I tried, I couldn't come up with any for this. And I think, when you pick, say, these examples here, it becomes fairly clear that this is probably always going to be true, though I don't know for sure. But it seems very hard to negate any of this. Because if A is the smallest, when you square it, you're timesing the 2 biggest sized numbers together. And of course, you're going to end up with a positive because it's 2 negatives multiplying. So that likely seems the biggest. And then here, you've got the biggest size number times the second biggest. And then here, you've got the biggest times the smallest. So it seems very likely, given that they're all going to become positive because they're all negative, seems very logical that this must be true. And likewise, this one's more obvious. To get something to multiply by another thing and be bigger than 0, either this and this are both positive, which can't possibly be the case because B is definitely negative, or this is negative and this is negative, but C plus A is clearly negative because A and C are both negative. So when you add 2 negatives, you get a negative. So this is clearly negative times negative, which is definitely bigger than 0, since none of the numbers are 0 themselves. So it seems pretty clear that these two are logically probably pretty unbeatable. This one is definitely wrong. When I multiply both of the sides of this equation by b, because b is less than 0, I'd have to swap the sign. So I end up with this, but this contradicts the original statement because c is supposed to be bigger than a. So this is definitely not true. Like this, this is just not true. But these two, I think, logically are. Okay, number 9, circular table. There's my round table. What's the smallest number of people sitting so that if someone sits down, they must sit next to someone. Now, initially, you kind of think, well, okay, so you just set them up. So this represents someone sitting down. This is an empty chair. Sitting down, empty chair, all the way around. Except you can do better than this. Because if you go someone and then 2 empty chairs and then someone, and then 2 empty chairs and then someone, you can't sit down anywhere here and be sitting next and not be sitting next to someone else. Because here it's next to this person, here's next to this one. So this is actually the best you can do. And what this is 13 copies. There are 40 chairs, and these are in batches of 3, right? XOO. So batches of 3, and now you have 13 copies of this XOO going around. But that only takes up 39 chairs, because of course 13 times 3 is 39, which leaves you, after you've done your final XOO, after you've gone all the way around, putting 13 people down in your proper places, leaves you with this blank space here. And you can't make that empty, because if that chair is empty, then this person or this chair is vacant with an empty next to it, either side, so someone can just sit there. So you have to fill that chair in as well, even though it's inefficient. And you end up with the 13 X's from the original 13 pans plus this guy, and you get 14 in total. Number 10, so we've got a quadrilateral labeled anti-clockwise PQRS. Which of the following is necessary but not sufficient? So let's just go through them one by one. So PQ equal to SR, so that side equal to that side. Well, I know that's necessary for a parallelogram. Like parallelograms have both sides equal and opposite. And both pairs of sides are also parallel. Now, PS parallels QR, so that's also completely necessary. This is just going some way to defining a parallelogram, right? So this is completely necessary because we know these have to be parallel, so do these, and these have to be the same, and so do these. So this is all necessary. Is it sufficient? Well, it's actually not, because I can just draw this, right? Where this side is the same as this. This is an isosceles trapezium. It's definitely not a parallelogram because that's not parallel to that. So these conditions are necessary for a parallelogram, right? Because they're part of what makes a parallelogram what it is, but they're not sufficient because you can just draw this with it if you want to. And it's actually completely unnecessary for me to continue because I found the one that is necessary but not sufficient. So you can, on your own if you want to, you can draw out some of these and work out why they're either not necessary or they are sufficient, but this is the one that meets those criteria. Number 11, arithmetic sequence, all integers, the sum is 20 after n terms. Which of these must be true? Again, must be true. Let's just come up with counterexamples. The first term in the series is even. There's a counterexample. That's an arithmetic series, and don't even try pretending that it's not. That's an arithmetic series that has 4 terms, add up to 20, and the first term is not even. So this doesn't have to be true. N is even, so the number of terms that you're adding up, does that have to be even? Nope. There's an arithmetic series where n is odd. The first 5 terms we're looking at here, they add up to 20. N is not even, so that doesn't have to be true either. Now, I actually got a little bit stuck trying to come up with a counterexample where the difference was odd. Notice here the difference is even, both of these, because the difference is 0. So what I did was I just broke out some algebra, and I said, well, what happens if you add the first 4 terms together? Apparently that's 20. Well, this is 4 A's and 6 D's. And now this is even. This is even. Well, actually, no, sorry. Divide everything by 2 first. This is even. This is even. Which means this must be even, which means D must be even. So that doesn't seem to be good. I've just shown that D must be even there because I must have even plus even equals even. But remember, that's when I chose N to be even. I chose 4 terms. So what happens if I choose N to be odd and get 5 terms? Well, I get 5 lots of A. You end up with 10 lots of D this time. And this seems more promising, right? Because this is odd, which means, because there's nothing here that tells me straight away that D must be even here. So what I'm going to do is I'm just going to choose some numbers that make it not. So let's just choose D to be 1, because 1 is obviously odd. N I've already chosen to be 5 because I added up 5 terms in this algebra. And A I'm just going to choose to be 2 because, of course, 10 times 1 equals 10, which leaves me 10 left over, so A has to be 2. And what happens when you just generate a sequence of this, where you have a difference of 1, so that's the sequence 2, 3, 4, 5, 6, and you're having 5 terms, add those up and they equal 20, so the difference doesn't have to be even. None of them must be true. If you just came up with this counterexample off the top of your head, then great, you saved yourself some work. But just think, when you're thinking something must be true, counterexamples. Just try and come up with counterexamples. If you fail, maybe do some investigative algebra until you can help yourself come up with a counterexample, or just prove the case entirely, whichever way ends up happening. Number 12. Most students in a college study maths. A teacher chooses 3 students random, and there are these 3 probabilities. At least 1 student studies maths, the second studies maths, or 3 study maths. Now, this question we should just be writing down the answer to, because look at these statements carefully. At least 1 of the students studies maths. That's quite a broad statement, right? Like, you can have as many as you want of the 3. You just need 1 of them to be true, but it could be any one. It could be the first, the second, or the third, or it could be the first and the second, because of course it's at least 1. Now look at the second statement. That's just a more stringent copy of the first, right? This one, you must have the second student do it, right? Which means that at least 1 studies maths. Like, that's the point. At least 1 student, in this case, at least 1 student studying maths. It's just a more selective one. The student has to be the second one, along with whatever you want on the others for the first and third. So this must be a smaller probability than that, because it's just a more carefully selected version of this. It's a smaller set, because this could be any one of them, whereas this has to be the second. This has got to be more likely than this. And likewise, when you get down to here, like, if all 3 of them study maths, then that means that in any case that you draw up where all 3 study maths, the second, of course, must study maths. Whereas this one, so the second one was just saying what the second can, and the first and third can do whatever they like. This one says the second must, and the first and third also must. So this is just a more tight version of this. And so the order for the probabilities is just the order that they're contained in, which is, this is the most likely, followed by this, which is just a subset of that, followed by this, which is just a subset of that. I'm going to put a video in the link that talks about another question just like this one, in case you want more detail to that kind of logic. It's called set theory. Number 13. So we've got this integral, and it's an overestimate. So this is what an overestimate looks like. When the trapezium goes slightly over the line, it happens for concave graphs. Okay. Which of the following is necessarily true? Now, sine of x is an odd function. What that means is that whatever it does over here, it does the same over here, except in the negative down below. So sine wiggles up here, up first and then down, and here it's going down and then up. But sine squared, now if we just square both sides of this, of course, when you square that, the 2 negatives go away, and when you square that, you end up with this, which means that sine squared is an even function. This is the definition of an even function. When you put in a positive x, you get the same number as when you put in the negative x, just like cos. So cos starts up here, starts going down, and it does the same on the other side. So sine squared is an even function, which means, well, why am I talking about that? Well, if you imagine integrating between a and b, I know this isn't sine, but it doesn't make a difference. When you integrate between a and b, if you flip those limits to be minus a and minus b, if the function is symmetrical around the y-axis, which I've decided sine of x is, then of course the integral must just be identical, which means if this was an overestimate, then this must also be an overestimate. Okay, so I think 1 is necessarily true because of the evenness of sine squared. 2 is much more difficult to analyze, I think. Here's my terrible sine of x graph. Now, what does sine squared look like first? Well, sine squared does this same kind of thing. Maybe it does it more steeply, but it doesn't really matter. It's just a sketch. Now, when you start going to the negatives, of course, when you square a negative, you end up positive again. So sine squared ends up going up and down, up and down. It never comes down here. It just ends up going up and down like this, right? So we end up with something that looks roughly like that. Again, just a terrible sketch, but roughly like that. Now, I got a little bit stuck here until I had a bit of a breakthrough, which is, how is cos squared related to sine squared? Well, through this amazing rule, right? Which means then cos squared is 1 minus sine squared. And so what I'm saying here is, to plot cos squared, I can just transform sine squared in this way. And what transformation is that? Well, I'm doing minus sine squared first. So I'm going to flip sine squared in the y-axis. So, sorry, in the x-axis. I'm going to flip it down the x-axis. And then I'm going to move it up by 1. Essentially, this is minus sine squared plus 1, of course. So let's pretend if we zoomed in massively to a place in sine squared, it looked like this. Now, the reason I've drawn it like this is because, remember, it's an overestimate when I use the trapezium rule. So I'm going to imagine I'm using the trapezium rule here. It's an overestimate. Now I'm going to try and draw cos squared from this. Well, first I flip sine squared in the x-axis because of this minus. So that's what minus sine squared looks like. And now I'm going to move it up by 1. Move it up by 1 here. Now remember, sine squared is bounded in between 0 and 1, just like sine is. So when I move this up by 1, it's going to be between 1 and 0 here. Because if the red graph is between 0 and 1, then the blue graph is between 0 and minus 1, which means when you move it up, it's between 1 and 0. But of course, this here is now a convex graph. So that there, which is the same as this here, is going to give me an underestimate because when I put the trapezium here, it's going to go underneath the line. So this is necessarily an underestimate, and both of them end up being true. Quite a difficult question to analyze, that one, I think. Number 14. Okay, so we've got a polynomial that is apparently increasing. So if you just take a polynomial, p of x and x on a graph, and you've got the points a and b, you want the polynomial to go up from a to b. Now, of course, that necessarily means that f of b is bigger than f of a, right? So I should have written p of b and p of a, but okay, I'm going to say it right now, again, out loud. This should be a p, this should be a p. I hope there's no confusion. But I mean, of course, this is necessarily true. That's what it means to be increasing, right? Is that it goes up from there to there. There is one exception to this, which is if it was like tan, where it goes from here maybe up and then down through here. But it's a polynomial, and polynomials don't do that. They don't have asymptotes. So this is definitely necessarily true. Now, I know that this one isn't true. I know the gradient at b doesn't have to be bigger than the gradient at a, because I can just draw this graph here. And now the gradient at A is much bigger than the gradient at B. So this definitely doesn't have to be true. And also, this graph actually also counterexamples this, because if you look, the gradient itself is changing faster in this section than in this section. Like, I've deliberately tried to draw the graph very flat along here, because a graph that's relatively flat and even flatter is changing gradient relatively slowly compared to one that's really quite steep and then getting less steep quite quickly. So this also counterexamples this, which is that the gradient of the gradient should apparently be bigger over here than over here, but that's not true. The rate of change of gradient here is much bigger than it is here. So this also counterexamples that statement. So it's only one that is necessary. There's a counterexample for the other two. Okay, some simultaneous equations here, essentially. Let's call these equations 1, 2, and 3, and let's do equation 2 minus equation 1. Now, when I do log minus log, of course, I can divide according to the power rule. And of course, 11 take away 7 is 4. I can cancel some stuff in here, and I end up with this equation. Now, what happens when I do equation 3 minus equation 2? Well, again, log of this minus log of that, you can divide the inputs here, that's the log law, and then you can cancel some stuff and you end up with this. And now finally, equation 3 and equation 1 to go. Same kind of thing, 15 take away 7 is 8 this time. I cancel all of these things in here and you get that. Now what am I going to do with this? Well, I notice both of these equal 4. So that means that log of AC over B equals log of BC, which also actually I guess equals half of this I've written, but I don't think I'm going to end up using that. Because of course this means that this input must be the same as that input. So AC over B must equal BC. Times both sides by b, cancel out the c's, and you get a as b squared. And what I'm going to do is I'm going to go back into here, and I'm going to rewrite a as b squared every time I see it. So if a is b squared, then that's a b squared, and that makes that a b to the 4. If a is b squared, then this is b squared squared, which is b to the 4, and another one there to make b to the 5. And here, this is again b to the 4, b to the 6 in total. And I get these three equations. And now I've made some progress here, that's good. What can I do now? Well, I notice this last one here is quite interesting because I can rewrite that one as b to the 2c all cubed, which seems good because this 3 then moves down here. And then I just divide everything by 3. And I end up with a new statement, which is going to be very helpful because if I call, say, this statement statement 4 and this statement statement 5, I can then see what happens when I do 4 take away 5. Again, I get this input divided by that input because of how logs work, and then 7 take away 5 is 2. But of course, that cancels with that, and that gives me a b squared. Now, of course, that 2 can move out to the front, divide both sides by 2, and what base does log b equal 1 at? Well, it must be base b, right? That's the definition of a log. So yeah, this took a bit of trial and error until I found a thing that made that work. There are probably loads of other ways you could do it, but I thought that was quite a satisfying way. Question number 16. Apparently, so here's some polynomial that intersects the x-axis at 2 distinct points, which means discriminant bigger than 0. I can find the discriminant of this very easily. It's just q squared minus 4 times p, which is just this. And now I'm going to move the 4p squared over. And now I'm going to square root this, but I need to be careful, of course, because when you square it, you can get a plus minus. And when you have an inequality and not an equals, that becomes quite awkward. But let's first square root and just pretend everything is positive, so the sign doesn't change. But now let's square root and say that what we had before was actually a negative 2p. Because, of course, going this way, if you times this by negative 2p, the sign has to change because you're times by a negative. And I know negative 2p is negative because p is positive. So I know that I must have to change the sign here. And this is good because this just gives me the equations of 2 lines, right? Q is the y-axis and x is the x. And p is the x. So this is essentially just the line y greater than 2x, which is this line here, line gradient 2, y-intercept of 0. But I want to be above that. I want to be above it. But I also want to do the same thing over here with q less than minus 2p. So I want the minus 2 graph, which is this one, and I want to be below that. So this is going to be the graph that matches both those descriptions. Okay, number 17. Only one of these things is correct. Which one is it? Well, okay, let's pretend this is correct, this statement number A. The problem with that is that if statement number A is correct, then statement number B is definitely also correct, right? If something is true if and only if x is greater than 1, it's true if x is greater than 1, right? So if this is true, then this is, and that contradicts exactly 1 being true, so that can't be true. Exactly the same here. If this is true, then this is definitely also true, which means this can't be true because only one of them is. So that can't be true either. And now what about these two? Well, the problem is, if this one is true, if something is true for x greater than 1, then something is true for x greater than 2, right? Because this is just a less specific version of that. Right? So this can't be true because it forces this to be, which means this is the only true one. So D, or the only one that can be true. Number 18, again, like so many questions before it, I'm going to sketch this. I know mod x looks like this, which means I know mod x minus 2, that's just been transformed 2 to the right. That looks like that. I animated this in wrong, but this one here, this black one, and this point here is 2 because of course it's been moved 2 to the left. Now this black one here represents a mod x plus 1. I'm pretending a is some number bigger than 1, so the graph gets pulled upwards, the gradient becomes steeper both sides, and it's been moved up 1, so this point is 1 here. Now I don't need this red graph, and now apparently this black graph is always less than this green graph, which doesn't work according to my picture. This black graph is bigger than the green graph. It's higher up, like all in like this entire area. So what I need to do is I need to actually say, well, A needs to be a completely different number that multiplies this mod in a downwards direction. So A needs to be a negative number, and it needs to multiply the mod so that it comes down like this. Because now this graph is indeed always less than the green graph. And now, what value of A exactly can I have? Well, if I draw the graph exactly like this is the boundary case, where this graph is just about less than or equal to the green at all times. And now this gradient here is just a rise of 1, run of 2. So the gradient is minus a half, which means that's what A must have been. And so A must be less than minus a half, anything less than that. If it's like minus 10, the graph is super steep like this, and it's definitely less than the green. So it's going to have to be A less than or equal to minus a half. Is the answer. Number 19, I've given this question out. I've made worksheets on this question. It's brilliant. So one way to do this might be to try and square out everything and get rid of these big square roots, but you don't have to, because what you instead want to notice is the way that they've given this is suspicious. It's sus, mate. It's sus. Like, why would they have an 8 plus a 1 at the end here and a 9 plus an 8? Why isn't this not just 17 and 9? Like, it's so sus. So what we're going to do is we're going to work out, well, the reason they've done that is because actually they're pointing us in the right direction here. They want us to do something. And what they want us to do is factorize this inner term here. Because that factorizes very cleanly to 2 root 2 minus 1, 2 root 2 minus 1. Of course, you can expand this out if you want to, but 2 root 2 times 2 root 2, well, 2 times 2 is 4, root 2 times root 2 is 2, so that makes an 8. Then we have a minus 2 root 2 minus another 2 root 2, which gives you minus 4 root 2, and a plus 1 at the end. And likewise over here, 3 times 3 is 9. 3 times negative 2 root 2 is negative 6 root 2, minus another 6 root 2 for minus 12 root 2, and then this times this, as already discussed, is an 8. But of course, these brackets are repeated, so you can write them like this. And now, just before you cancel the square root and the square, you just want to be incredibly careful just to make absolutely sure that neither of these two inner terms are negative. Because if they're negative, when you cancel the square and the square root, you have to times them by minus 1 as well. But actually, I mean, 2 root 2 minus 1 is clearly bigger than 0, because this is like around, I mean, it's slightly less than, it's bigger than 3, slightly less than 4, but easily positive. This be a bit more careful with, but this is about 1.4, which makes this about 2.8. 3 minus 2.8 is positive, so that's fine. I can just cancel the root and the squares, and then of course this cancels with this, and that makes a minus. That makes a positive 2. Okay, nice. Question number 20. Okay, so this opens up a Pandora's box a little bit, but I'm not gonna go into it in too much detail. First, I'm just gonna get a feel for the problem. Let's just draw some graph. This one. This is always the one that I like to, just the x squared graph. I like to transform it a lot. I think it is a good thing to just start with. I'm going to reflect this graph in the y-axis. Well, nothing happens if I do that. And then I'm going to translate it 2 in the negative x direction, and it ends up there. So that's going to be g of x in this example. The other way that I'm going to do it is translate 2 in the negative x direction, so move it first, and then reflect it in the y, so it ends up going over here, and that's going to be my h of x. Now, in this example, I don't know why that's covered in green. In this example, the two things are not the same. H and G are not identical. So this is not an example that they're interested in. But that's kind of useful in some ways because, of course, this graph here follows this rule, say, right? It's symmetrical in the y-axis, which essentially is what this rule is saying. So this cannot be a necessary and sufficient condition because it doesn't work for this example. So at least I can get rid of that, and maybe I've made a bit of progress. I mean, if your aim is to guess at some of the questions, of course, you want to have as few options to guess between as possible. So getting rid of some is a good idea. So you could do some more drawings, and you could draw some graphs that follow these rules and see whether they work or whether they don't work. I'm actually just going to do it a much quicker way, which is to do a bit of algebra here to say what happens when you actually do this to f of x. Now, when you reflect it in the y-axis, that's f of minus x. And when you translate it 2 in the negative x, that's when you add 2 to the input. So notice how I've added 2 into this input here. It's not minus 2, I'm sorry, it's not minus x and then add on 2. I've changed the input because all the inputs have moved 2 to the left. I've changed those to x plus 2. And now I'm going to sort out the minus to give me this kind of expression. And now doing it the other way, f of x here, you shift it first. So that becomes x plus 2. And then you flip it in the negative x-axis. Now be careful here. What I haven't done is I haven't done negative all of the input. I haven't negatived all of x plus 2 when I flip it in the y-axis. And there's 2 reasons for that. Firstly, because if I know that if I did negative all of x plus 2 here, rather than just the x, I would end up with that expression. And I know I can't just be getting that expression because it doesn't work for some graphs. And secondly, if you were to just negative this entire thing, what that actually is a reflection in the x equals minus 2 line, whereas I want to reflect in the x equals 0 line. So you just negative this x here, which gives you this expression. And essentially the question is saying, when is this the same as this? And the easiest way to sort this out is to just make a substitution and say, let's just make u this thing, because then I just have f of u on this side. And now what does this become? Well, I can add 4 to both of these to get this. And now I can replace this with a u plus 4. So this makes f of u equal u plus 4, which is this condition here. And so the answer is B. Quite a difficult question, but I mean, it's question 20, so you're expecting it, I guess.